All right, next lecture, lecture 25. We are still going to be talking about Brayton cycles in the later stages, the later pages of chapter 9. And so we will go again quickly over the ideal cycle, and we're going to talk about more ways to increase the efficiency. Increasing efficiency will be done here by regeneration, reheat, and intercooling, and we'll see what that is. So a quick reminder, at the end of the classroom lecture last time, we added irreversibilities to the classic ideal Brayton cycle. So in the ideal Brayton cycle, you had a compression, isentropic compression from 1 to 2. Now you're going to have an isentropic compression 1 to 2s, and then a compressor efficiency, given by this, gives you the relation between 2 and 2s. Then we had, ideally, a heating at a constant pressure in the combustion chambers. But of course, in practice, there is a little bit of loss of pressure in that combustion chamber. Let's ignore that. Then we had the isentropic transformation in the turbine from 3 to 4, which is hampered by a turbine efficiency, an isentropic efficiency of the turbine, so that instead of going from 3 to 4s, we go from 3 to 4, and you know how to go from 4 to 4s using this isentropic efficiency, and then from 4 to 1. So we had an exercise on this last time. Let's now move on to the effect of the pressure ratio. So I told you that one of the important design parameters in all these Brayton cycles is the compression ratio, the pressure ratio in the compressor stage, which is, of course, the same compression ratio that you end up with in the turbine if the cycle is ideal. So we showed you in the cold air standard analysis how you can have a thermal efficiency that increases when you increase the compressor pressure ratio. In fact, at a compression ratio of 1, which means no compression, nothing works, of course. So you get a constantly better thermal efficiency. The problem of that is that it comes at the expense of a constantly increasing turbine inlet temperature. And of course, at the end of the day, the maximum temperature you can have, the higher the temperature can have, the better efficiency, Carnot. But the maximum temperature is set by the limitations of the metals that you can use at the end of the combustion chamber, and more importantly, in fact, at the beginning of the turbine stage, which are extremely sophisticated alloys, typically single crystal titanium with cooling channels in them and things like that. Nevertheless, there is a limit to how high you can use T3. So if I now look at the TS diagram, and I were to look at efficiencies of cycles that would go from 1 to 2 to 3 to 4, back to 1, versus the efficiency of a cycle that would go from 1 to 2 to 3 to 4, back to 1, you see that they have very different amounts of work, but you have also a very different amount of efficiency. Now, we have a limit to this T3, that is turbine inlet temperature, that is set by the maximum heat, maximum temperature that the metallurgy of your turbine blades can actually take. So we have to optimize these cycles for the value of T3 to be fixed. So T1 is fixed and T3 is fixed. Now the question will be, well, what is the most efficient gas turbine? And of course, another question would be, what is the most powerful gas turbine? So if you consider this to be the area that is the amount of work that the net work that the turbine will produce, whereas the curve from this intercept here, 2, 2, 2, 3, 2, 4, is going to be the amount of heat that you put in other words, the cost of your fuel, then the efficiency is the ratio of this blue area to the area from here up there. Well, you can see that a cycle that's high and narrow is going to be more efficient, simply because this curve curves up. Whereas a cycle that is long and wide is going to have more power because you have more area here. But that power comes at the expense of more fuel. So one can optimize these things for power, which you will do in transportation applications like turbines that are used in airplane propulsion, or you can optimize this for efficiency, which we will do for turbines that are used in ground applications for power generation. Now, I will then demonstrate using cold air standard analysis during the class on the blackboard, because that will slow me down, that the actual optimum compression ratio, which is the best ratio between the high pressure stage and the low pressure stage of the compressor, is scaled as T3, which is the maximum temperature you can put in, divided by T1 to the power K over 2 times K minus 1, where K is the ratio of Cp over Cv. So a typical number for K at air is about 1.4. And that gives you one design parameter that is really fixed by the metallurgy of your blades. We'll do this in class. It takes a little bit of algebra, and I won't do it here. Let's now look at other ways to optimize the efficiency of a gas turbine. Well, the first is called a regenerative cycle. So the concept of the regenerative cycle is that you have air that comes from the compressor out here, and so the air is a little bit hot. It's at temperature T2. In a classic cycle, you feed T2 straight into the combustor, and you go from 2 to 3. And so that's nice. But the hot air that comes at the exhaust of your turbine, T4, is typically at a higher temperature than the air that you feed out of T2. So that means that you have the opportunity of taking enthalpy, or heat, out of point number 4 and putting it back into point number 2, which in this heat exchanger, so we're going to take T4 minus Ty. The H4 minus Hy is an amount of enthalpy that we will feed back in the airstream between the compressor and the combustion chamber, thereby preheating the air at point number X through this heat exchanger. So we will get the air from 2 to X warm by using air temperature and enthalpy that comes from point number 4 and having this heat exchanger here between X and that. That means that then the fuel is only needed to get the enthalpy from X to 3. In other words, you need to fuel only the part X to 3 of the cycle. The amount of heat you put in then is going to be from this T equals 0 axis to X to 3 to 4 down. And this area from here to here to here to here is smaller, of course, than the area from here to here to here to here, which you would have if you didn't preheat it to X, by an amount that's really this amount of area here. All right. So let's write these equations down. Qin then becomes H3 minus Hx, which is clearly less than H3 minus H2. That's what I write here. Now, then you get the air to a temperature Tx, and Tx has to be smaller than T4, because the second principle of thermodynamics dictates that you cannot get this air at this point hotter than the air that's at that point, since you have to have heat go from here to here, and heat only will stream from a higher point to a lower point. Okay, so that sets Tx smaller than T4. Next, we look at the efficiency of the cycle. Well, the network, turbine minus compressor, is of course H4 minus H3 minus H1 minus H2, just like was before. But we divide this by H3 minus Hx, which is smaller than H3 minus H2, and therefore this ratio is larger than this ratio. Your efficiency has increased. Now, that needs to be calculated in exercises that use regenerative turbines, and that's a little bit harder. So let's consider this heat exchanger, and let's assume that you have a counterflow heat exchanger. So you have hot air stream in and out on this side, cold air stream in and out on this side. If your heat exchanger is absolutely perfect, the temperature here will end up the same as the temperature there, and the entire enthalpy that you will have dropped in this airstream, you will have recovered in that airstream. We're assuming, of course, that the volumetric flow rates, that the mass flow rates are the same, which they are because it's a closed cycle. If you look at the turbine, in the air that goes in here follows this path, and it's the same air that goes there. So the mass hasn't changed. Now, a real heat exchanger is not exactly like that. There is an efficiency to the heat exchanger because you have a certain difference. So here is along the length of the heat exchanger the temperatures. The cold air comes in here, the hot air goes in here, but by the time you're at the exit, this point here corresponds to this flow here, it's a little bit colder than the temperature of the air in. So basically, this temperature, which is Tx on your diagram, is a little bit below T4, which is that temperature. And the efficiency of this heat exchanger, which is called the regenerator, hence the index REG, is Hx minus H2 over H4 minus H2, which is basically represents the loss of temperature between X and 4, the loss of temperature here in the heat exchanger. All right. So now these regenerators are that much better. They have that much higher regenerator efficiencies as the areas in the heat exchangers are large. Now, large areas means large components, means lots of weight and lots of cost. And therefore, this is usually done when efficiency is at a premium and where weight doesn't matter that much, or plants that work all the time, where cost is probably a secondary consideration compared to, for example, fuel economy. So this is commonly done in large stationary power plants, but it's not commonly done in gas turbines used for applications on airplanes, because there they have to be compact and light. And so this would make much less economic sense. Now let's look at how you will solve a regenerative ideal gas turbine cycle in a problem. So you see that with this, your heat exchanger here sends its air out at point number y. So reality is, if we are going to make a cycle, the cycle is going to from 1 to 2, 2 to x, x to 3, 3 to 4, and then 4 to y. So this is the heat out. It's hy minus h1. And y is necessarily below x, because you have dumped the air in here. It's actually, it might be below 2, but not necessarily so. So in fact, when you have a turbine like this, you have two unknowns, Tx and Ty. What matters in the analysis is not only the temperature and the enthalpy at x, but also the enthalpy at point 1, y, because that goes into your equations. So we have two equations. We have, on the one hand, the energy balance equation in the regenerator, which tells you that the enthalpy that you add to the input stream, so Hx minus H2 is what you increase the enthalpy for in the incoming stream, must be equal to the enthalpy that you put out of the stream that heats the other stream up. So the enthalpy H4 minus Hy. H4 minus Hy much equal Hx minus H2, the mass flow rates are the same. So this is one equation. And then the other equation is the effectiveness definition of the regenerator, which we just had before. Eta regenerator, which will give you 80% or something, Hs minus X minus H2 over H4 minus H2. So you have two equations, two unknowns, Hx and Hy. The fact is that when you try this in an actual experiment, in an actual problem set, you're not going to be able to find a direct linear solution. You're going to have to solve these two equations for two unknowns simultaneously. I'm going to have to solve this for Hx and plug it in here and solve for Hy, etc. Put that in your cycle. So two equations, two unknowns have to be solved by hand. You don't have a 1 to 2 to x to 3 to 4 to y. You can't just go step by step, 1 to 2 to 3 to x to 3 to 4 to y. You have to really write a set of two equations. So now my little accounting table won't work anymore. You're going to have two equations, two unknowns. Sorry. This is where computer solutions are easier, but we don't have them handy for exams and things like this. Let me move on to the next part of this class on techniques to improve efficiency. The next is the reheat. So here's my compressor, one single compressor, and I will go back to a single combustion chamber. So in your compressor, you have the isentropic compression, PR2 gives you PR1, P2 over P1. Very good. And you have compression ratio. Okay, now in the first combustor, you give in a certain amount of heat and you send that to a temperature T3. But once again, T3 is really limited by the metallurgy, so you would like to have T3 as hot as you possibly can get the frame, 3000 degrees Kelvin or something, but there is no way, there's no material on Earth that will maintain these temperatures without burning up. So you have a limited T3. Well, then what you do, so you go from 1 to 2, 2 to 3, and this is limited. Okay, so you go in two stages with your turbine. You have a first stage where you go from 3 to A, and you don't go all the way back to P1. You go to an intermediate pressure, PA, after which you send your air back into a second combustor, a reheat combustor, so you have more Q in here, and you go from A to B, A to B, A to B. And then you come back down at 4, and the rest of the cycle is the same as before. So now what you have is an additional piece of work here that you can carve out. This is the area A to B to 4 to 4 prime, is an additional work that you can carve out. And you have as heat 1 to 2, 2 to 3, and then again A to B to 4 to back to 0 here. So your efficiency is H3 minus HA, that's the enthalpy of the first turbine, plus HB minus H4, that's the enthalpy that you get out of the second turbine, minus the work of the enthalpy that you have to put back in the compressor, H2 minus H1. And the heat, well, the heat comes in two steps. This heat goes in, that's H3 minus H2, and you have to add HB minus HA, which is your second heat. It turns out, as you will see in details when we do exercises, that this is actually more efficient than not have the reheat, at least if you fix T3, which you always have to do. So reheat works, and another technique that works is intercooling. Well, what is intercooling? In fact, you can see some trucks with gas engines or diesel engines, and they will then have turbocharger, and some of them advertise intercooled on the turbochargers. It's exactly the same principle that we're going to have here. An intercooler increases the efficiency of a pump or a turbine or a compressor. And here's how this works. Let's go back now to the expression of work in an open system, so chapter 4. In chapter 4, you saw that if you have an open system, the work is actually the intercooler between 1 and 2 of VDP. Remember closed system, PDV, here it's VDP. So in a PV diagram, and you go between 1 and 2, the work will be this area, the green area between, which is VDP. It's the integral between the curve and, now in this case, the ordinate axis, because the independent variable is P. Well, and we have also learned that work is not an equation of state, that it depends on the path taken. Well, it turns out that if you take a path that's an adiabatic compression between 1 and 2 prime here, that path is different from a path that would be following an isotherm. So if I take T1 equals T2, arbitrarily I put T1 equals T2, that path would be between here and here. And you can see that the work between here, this point, that point, and that point is smaller than the work between this point to prime, that point, that point, that point. So basically, if you could make an isothermal compression instead of an adiabatic compression, it would cost you less energy. That compressor would take less work. Good. Now, we don't know how to make an isothermal compressor, because usually when you compress something, it heats up. So the best we can do is try to pick some intermediate temperature where we will cool the gas again back to the initial temperature. And that's what an intercooler does. So here's the intercooler. We divide the compressor into two stages, and at some intermediate temperature and pressure, say C, we send the gas through a heat exchanger where we cool it with outside air. And that decreases the temperature. TD is lower than TC. So TD, if you want, is closer to T1. And if you, of course, could make the compression between 1 and 2 all the way isothermal, that'd be ideal. But you can't. This sort of makes it halfway isothermal, if I dare say. So we go from 1 to, instead of going from 1 to 2 with one single isentrope, we're going to go from 1 to an intermediate point C here. And then in a PV diagram, we're going to, this is a heat exchanger, so P is constant, follow a horizontal line between C and D, where we decrease the temperature. We go closer to a constant temperature that would be equal to T1. We go here. And now from D to 2, we do the second stage compression. Oops. Well, if I now calculate the work from 1 to C to D to 2 to A to B is the pale blue curve. It's smaller by an amount that's this dark hashed blue curve, the work that it would have taken to do a classic isentropic compression. That work we are going to use in this intermediate stage. Here's the same thing in the TS diagram, and it's the same picture. Okay, now once again, we have to optimize the pressure at which we're going to locate this intercooler heat exchanger. So PC. Well, that again can be done using standard air analysis, cold standard air analysis. So we're giving you an inlet temperature pressure P1, and we're asking you to build us a compressor that will reach a pressure P2, and we can allow you to use an intercooler at some pressure P intermediate that you can pick. So what do? I'll do this again during the actual lecture on the blackboard because that slows me down. But there is an optimum value for this intermediate pressure such that Pi over P1 is P2 over Pi. In other words, Pi squared is the product of P1, P2, or Pi is the square root of the product P1, P2. I will demonstrate that on the blackboard, but this is the pressure at which we like to divide the compressor stages. So this is the first pressure, this is the second pressure, and this is the stage location of the pressure that we put for the intercooler. Thank you.